You'll find 1,000 different ways to do exactly the same thing. It really won't give you a good insight as to how they're getting it done. They go, well, here's the code, download it. It may be commented, it may not be. So, do I hear the sounds of data sheets being read? No, I don't. Okay, anyway. Here are the current pin assignments. The pins they're numbered on the chip, 1 through 8, but they're also called PB0, 1, 2, 3, 4, and there's a PB5, okay? The remaining pins on the ATtiny are VCC, ground, and reset. PB5 shares a pin with the reset pin. Okay, now, why those pins? I mean, this actually kind of needs to be like this. There's a little wiggle room, there's a little bit of rearranging you can do, and in theory, you could do it almost completely arbitrarily because it is a programmable controller and you can assign which I/O pins do what to a certain degree, but there are strengths within the chip and resources within the chip that you need to know about so that you can make intelligent decisions on doing that. The servo outputs require precision timing pulses. Okay, there's a timer counter peripheral in the chip. Now it's only an 8-bit counter, but it also offers PWM outputs on 2 channels. It compares, you can set 2 variables, and when it matches the counter value, you can either set or reset one of the output pins. There's many, many modes that it supports, and the one I chose lets it send out a programmable width pulse on a certain update rate at a certain frequency. It's very easy to set up. It only takes about 2 or 3 lines of code, and to set the pulse width, you just literally write to a register, which when we get into the programming part, you'll see is it looks like you're assigning a value to a variable. You just say the register name equals 37 or 15 or whatever number you want, and that changes the width of that pulse. And then the hardware keeps doing that for you. You don't have to go back. You go, oh, I got to start that pulse again. Oh, I got to time that pulse. Oh, I got to turn that pulse off. You don't have to do that anymore. The hardware does that for you. And there's 2 pins for that, so we have the left and the right. So it's a good match. So you'd want to use those. We talked about the analog inputs from the cliff detectors. This chip actually has a 4-channel analog to digital converter built in. It can measure a voltage between ground and its supply voltage, or between ground and an internal band gap reference that it has available, which is like 1.1 volts, depending on what your range is, and turn that into a number, a 10-bit number, which is very handy to have and be able to read. Instead of having just is it on, is it off with the digital input, you've got all the 1,024 levels in between. It's not all the way on, but it's only about 10% down. You can do measurements like that. That leaves only the infrared LED that we're using, and in this case we're using 2 of them, but we're tying them both to the same output so that we drive, when we turn on the LED to give it some illumination for the sensors, it's actually turning on both of them at the same time. And we could have used any one of the pins for that because that's a simple I/O function, input-output function. Each of these pins on this device, because you read the data sheet, you know that it can source or sync up to 40 milliamps, which is plenty to light up any LED, even an infrared LED. We don't use PB5 as an I/O pin because it's complicated. I'll get to that in a second. If you really want to know, you go, but there's 6 pins, let's use 6 pins. Here's a way of getting a tool chain set up on your computer if you have Windows. And it turns out most people do. Maybe not most of the people in this room, but the average person that has access to a computer has access to a computer that runs Windows. The official, when I wrote this up for the class in January, the prevailing wisdom was on Windows, you use a package called WinADR, which is a collection of free and open source tools that supported the GNU GCC compiler, which is ported to this chip. You can write programs in C, Fortran, Objective-C, several other variations, and program them into code that this chip will be able to execute. You download and install this. This puts all the compilers and things like that on your system, makes them available. Then you would go and download another tool that's free, as in beer. It doesn't cost you anything to download it, but it's a proprietary product from Atmel. It's called AVR Studio. It's a fairly nice and well-supported IDE, or integrated development environment. It gives you a text editor and lets you link, your compilers and your make files and all that. Does a lot of that work for you in the background. Makes it easy to start projects, document projects, and compile and get the code into your chip. And again, it's free. Both of these big downloads, close to 100 megabytes a piece. So if you don't have cable or DSL, go hang out at your buddy's house or take them out to lunch or something, and get it that way.
Or buy it.
Hmm?
Or buy it.
I'm sorry, I can't hear you.
Buy it?
No, you can't buy it.
Oh, you can't?
No, none of these are for sale. These are all free tools. They're all only available by download for free. I mean, I'm sure you can
I
pay
was buy a DSL, I guess is what.
Oh, buy.
Oh, buy DSL. Yes.
I suppose that's an option too.
Yes, you can. You can go if it's available in your area.
Okay.
So I live out in the country, and it only recently, became available. Believe it or not.
That's a long drive to your neighbor's house, yeah.
It's actually out of wireless range.
Right.
So. Then the third part of the tool chain is going from the computer to this chip. Now, I don't know if you happen to notice, but at the end of the chip on this board, there was a little 6-pin connector, and that's what this little cable is attached to, and that goes to a programmer. That goes to a device programmer. Now, here's an example of a very low-cost device programmer that you can buy on eBay for $10, and that includes shipping. Okay, they go up from there for $25, $30, $35. You can buy a brand new Atmel branded, device programmer from any of the major distributors, Mausers, DigiKey, anybody. And you can go up. Yeah, I mean, you can spend more money on that, but you don't need to.
Well, for $50, you can get the Dragon, which then, if you get really serious, you can actually step through your code and debug it and stuff.
Yes, and that's a good point. Yeah, it's $49. It's called the AVR Dragon, and it supports what's called the debug wire protocol, which lets you actually debug this chip using in-circuit emulation. You don't need a separate emulator device. It actually can talk to the registers in the chip, single step through your code, look at variable values, modify individual bits and registers. It's handy. But you've got to pay $50 to get the adapter. It's not a open protocol.
Yeah, and you do have a simulator in AVR Studio that you can use. It's not really using your chip, but it's using a.
Oh, there is a simulator. Yes, there is a simulator.
There's 2 simulators.
Well,
Yeah.
there's Simulator and Simulator 2.
Yes.
Yes, and Simulator 1 is no longer supported and actually doesn't have the ATtiny13A in it.
Okay.
So Simulator 2 is the current one. But it's only good for certain things, because to create any sort of input stimulus for you, create what's called a stimulus file, it says after this many clock cycles the signal goes to 1. It's very cumbersome. There's no support for it.
You can set an ADC value or something like that, but that's about it.
You can, yeah, and you can sort of look through, trace through the logic of your code if you fake some of the inputs, things like that. So it has good value when you're, like, say, wanting to count cycles in a loop or need some nitty-gritty information like that. But if you really need to debug your code, the AVR Dragon is the cheapest way to get into that. Although I've seen some third-party emulators, I don't know how well they work or if they support that protocol or not. But again, starting at $10 or less, just depending on if you catch one on sale, you can get these, and they come straight from China. Now, we have to jump a chasm here. So far, all we've done is written code and either simulated it or thought about it or drawn some flowcharts. We've changed those bits into actual volts on the robot. We're going to start with a really simple example, which you're just going to have to take on faith, because I didn't bring anything to show it to you. I'm not going to show you how to blink an LED. Well, I'm not going to show you an LED blinking. I'm going to show you how to blink an LED. It doesn't really take a whole lot of code to do it. Once you have all that software installed, it's only really like 10 or 12 lines total, and you'll see, not very intimidating to do it. But just to give you a quick overview of what you get in that little chip for $1, $1.50. You get an AVR RISC processor that runs up to 20 megahertz. 1K of flash memory for program storage. Now that's 1K bytes. The instructions are 16 bits, so it's 512 instructions. So not a lot. Now the bigger parts, such as the one that's running in here, actually have 8K of memory, which is what the original Arduino had. So you know, it's a fairly capable little chip. In fact, I heard, and I haven't investigated it myself, I heard it from a friend of mine, they've ported the Arduino environment to the Tiny85. So, very interesting. I mean, if you only need 8 pins, that wasn't good at all. Fix me, please. One moment, please. It'll be fun. It'll be fun. We have our best men on it. I'm hitting the wrong buttons is what I'm doing. Okay, thank you. Excellent. Back where I was.
If you only need 8 pins.
If you only need 8 pins, you can run in the Arduino environment, which is has millions of examples, and hundreds of thousands of people using it. And